Let us look at the evaluation of the solute sources. The solute fluxes can be separated into crustal, sea salt and snowpack derived components as follows. All nitrate can be assumed to be snowpack derived. All chloride can be assumed to be sea salt derived. Sea salt contribution to fluxes of calcium 2+, Na+, Mg2+, and K+ can be estimated from chloride fluxes by using standard seawater ratios. A snowpack derived sulfate flux can be estimated from the chloride flux. So these are all the different ways by which we can identify what are the individual concentration of the ions that are present in the aqueous systems. Let us look at partitioning of the bicarbonate flux. The flux associated with the coupled sulfide oxidation carbonate dissolution reaction. So that means generally all crustally derived sulfates are based on this particular process. It yields one equivalent of bicarbonate and 2 of calcium 2+ and or Mg2+ for each equivalent of sulfate. The flux associated with the carbonation of aluminosilicate minerals. All dissolved silicon and crustally derived Na+ and K+ were produced by carbonation of aluminosilicates. So this is how the partitioning of bicarbonate flux works. So let us look at how do we actually collect the sample and analyze to understand what is actually happening. So the collection is mainly happening near the main subglacial outlets, and the water samples are filtered and non-filtered sample. So people actually carry out filtered and non-filtered sample. And early melt, summer, early winter are the time when the waters are actually collected. That means water is not frozen, they are in the liquid form. The measurement of pH, conductivity, alkalinity in the field, that is immediately at the time of collection, and in the lab after a couple of months, maybe during this entire process the collected water samples are stored in the dark, low temperature and away from sunlight. So this is how people go to that Arctic region, they collect the water sample, they filter it, and there is also another unfiltered sample, and they measure pH and other things at the site, and also they will take the water to the laboratory and they analyze in the later part. The pH is measured using acidimetry titration, that is when the endpoint is 4.2 to 4.5 pH, that is called methyl orange alkalinity or M-alka. And if the pH is at 8.2 to 8.3, that is called the phenolphthalein alkalinity or P-alka. So the different equations are given here. The M-alkalinity measures the concentration of hydroxide ions and bicarbonate ions and carbonate ions. The equation is given like this, that is M-alkalinity is equivalent to the concentration of hydroxide ion minus the concentration of protons plus the concentration of bicarbonate ions plus 2 times carbonate ion concentration. So that gives the total value for M-alkalinity. And when we talk about P-alkalinity, that is phenolphthalein alkalinity at the pH 8.2 to 8.3, which comprises of hydroxide ion concentration, carbonate concentration and carbonic acid are actually present. So this is the equation given for P-alkalinity. When we want to calculate the dissolved inorganic carbon, what we have to do is subtract P from M. That means P-alkalinity is subtracted from L-alkalinity. So which directly gives there is no hydroxide ion concentration. So which clearly tells that we are only dealing with carbon. That is inorganic carbon is only given here. They are carbonic acid, bicarbonate anion and carbonate anion. So this gives the total dissolved inorganic carbon that is present in the water which we are analyzing. So how to analyze the samples? Basically the concentration of the major cations Na+, K+, Mg2+, Ca2+, the trace elements manganese, nickel, iron, aluminium and dissolved silicon can be determined using AAS, that is atomic absorption spectrophotometry. Major anion concentration, that is chloride, nitrate, sulfate, were determined using ion chromatography. So these are all the two ways by which the cations and anions can be analyzed that are present in the water samples. There is a major method which people generally use, that is called dye tracing. Here, how the dye tracing actually works. A known quantity of 20% rhodomin WT was poured into a moulin at a predetermined time by a person not involved in the sampling. That means you go to the Arctic region and pour this dye at some particular place, and you are going to measure how much time it takes to reach to some other place where you are actually going to collect the sample. So you know the distance between the places, the time taken for the dye to travel from one place to another place. So based on that, people study. So that is how the dye tracing actually works. So during the first several hours of the test, the samples were taken there at intervals ranging from 1 to 30 minutes, that is depending on the change in the dye concentration. If it does not dissolve and disappear, then people allow longer time to analyze, and if it is dissolved and it is completely disappearing, then they will do the analysis very quickly. The sampling was initiated before measurable concentration of dye reached the sampling site. So first you put at one place and then you collect it at a different place. Once concentration had fallen below 0.5 parts per billion, the sampling interval was increased and the sampling was continued for at least an additional 12 to 16 hours, and in some cases up to 24 hours. So people keep on monitoring how much dye is actually present. Then the samples were analyzed in laboratory about 1 kilometer from the site of the toe of the glacier. A fluorometer was used. Basically, they calibrated using standard of known concentration. So this is how the dye tracing actually starts. Then let us look at what is this rhodomin WT which was used. There are two major rhodomins which are used for studying colorimetrically. So what are the chemical structure of the major two compounds? One is rhodomin B, which is called basic violet 10, and the other one is rhodomin WT, which is called acid red 388. So rhodomin B is basically a xanthine dye with the basic properties, whereas rhodomin WT is a xanthine dye with acidic properties. What are their photochemical stabilities? The rhodomin B has a moderate stability, but they can degrade under UV light and over time. So this is having a limitations. We will look at what is the limitation. Whereas the rhodomin WT is having high stability towards photochemical degradation, and it is more stable under UV light conditions. So this is a very, very important thing. That's the reason people use rhodomin WT in the dye tracing analysis in the Arctic region. And when we look at the fluorescence intensity, rhodomin B and rhodomin WT both have strong fluorescence, and even at a low concentration they fluoresce very effectively. And the excitation wavelengths are a little bit different for both the things. When we talk about the spectral range for rhodomin B, it is near UV and which is not well covered by remote sensing. Whereas for rhodomin WT, this is in the visible range, which is well covered by the remote sensing satellites. So what are the applications? These are rhodomin B is widely used in tracer studies but prone to photo degradation, though this is one of the major limitation. Whereas rhodomin WT is basically preferred for tracer studies in surface water due to higher stability. So what are their remote sensing capabilities? Rhodomin B is less suitable because they degrade under UV absorption. So that's the reason this is not generally used. Whereas rhodomin WT is well suited for remote sensing because both the excitation and the emission wavelengths fall within the visible spectrum. So we can actually visibly see this. And the major advantage of rhodomin WT is they have longer lasting in natural conditions, better suited for environmental field studies. Whereas what is the major limitation of rhodomin B? This is susceptible to photo degradation and fading over time. So that's the reason people don't use rhodomin B for the environmental studies. They prefer rhodomin WT. But one major concern is whatever the results which are available for both rhodomin B, it is shown that rhodomin B is more toxic than WT. But there is a large data gap, especially with regards to actual ecotoxicity studies of rhodomin WT. So this is one of the major limitations even when we are using rhodomin WT. So how do we continue the dye tracing studies? So from the values, a concentration time curve will be generated and analyzed because we have actually dropped dye at one particular area, that is the moulin areas, and they are collected or sampled at a very far off place, and once the different collection of water at different times are done, then people use a concentration time curve to analyze how much time it takes for the dye to reach sample site. So the multiple peaks in test may be attributed to braiding of the englacial subglacial conduit systems. The decreasing breadth of the curve is the early part of the 1985 melt season reflects a decreasing in disparity. So this is where people started doing that analysis in the early 1985. The variation in the time to the peak concentration reflects variation in flow velocity. So this is how we can find out how the dye is moving from one place to another place. And some of the calculations are given here. There is a paper which talks about this in an elaborate way. So the diffusion equation for longitudinal dispersion is long straight pipe is given by Taylor. This does not include the process contributing to the tails. So the equation is given by dC by dt is equal to d dou square C by dou x squared, where C is the concentration of the dye, capital D is the coefficient of longitudinal dispersion for a coordinate system moving at a mean flow velocity, d by dt is the material derivative, and t and x are the time and distance along the conduit. So instantaneous pulse of dye injected at time t0 is approximated by the delta function has the following analytical solution, which is given by this one, where q is the discharge, which is an assumed constant, u is the flow velocity, v0 is the volume of the dye injected. So based on that, we can actually calculate how much is the dye is being present in the water, and from that we can find out what is the time taken for it to travel. So if we assume that T1 and T2 are the time when C concentration reaches half of its peak value, Cm is the during the rise to the peak and during the following decline from peak respectively, then what we do get is U is equal to x by Tm. When x is equal to 1 kilometer, we have this particular equation. When Tm is the time to the peak and we solve for d, we get this final equation. Using this equation, we can actually find out the flow velocities and the dispersive characteristics of the englacial and subglacial hydraulic systems which we are studying.